Normally when we sit down to do one of these, we've got maybe a book, a few articles. We're trying to get our heads around a subject. But today feels a little different.
It feels heavier.
Literally. I mean, we're looking at a stack of what look like confidential strategy reports, technical white papers from companies like Electrobit, semiconductor market forecasts, the works.
Right. And the whole premise for this deep dive is unique. We're not just, talking about the future of cars in some abstract way.
No, we're simulating a very specific scenario here.
We are. We're placing ourselves and you, our listener, at a very precise moment in time. The date on our report is today, Wednesday, February 18th, 2026.
2026. So the context here is that everything has changed, and it's changed dramatically in just the last 2 years.
And if you're listening to this, we're framing this as if you are the client.
Right. You're not just a passive listener. You are a senior technology strategy consultant, or maybe chief engineer, a decision maker at let's say a legacy automotive powerhouse.
You've got a massive budget, a board that's getting nervous, and a problem that feels like it could, sink the entire company.
And that problem isn't the chassis. It's not the powertrain.
No, it's the code.
It's the digital brain. We've been through all this material, and the headline is, it's pretty stark, isn't it?
It is. The era of the hardware-first car is officially over. Dead.
If you are still building cars by stamping metal first and then trying to cram the software in later, you are already a dinosaur.
You're extinct, you just haven't fallen over yet.
So our mission today is to deliver what the consultants love to call a top-down MECE analysis of the global in-vehicle infotainment landscape. Can you just quickly unpack MECE for us?
Sure, it's classic McKinsey speak. It stands for mutually exclusive, collectively exhaustive.
Which means?
It basically means we're going to cover all the bases, we won't repeat ourselves, and we're going to structure this so logically that there's simply nowhere for the real problems to hide.
I like that. Not hiding places.
Yeah.
So let's start with the why. Why is this a crisis now? I mean, cars have had software for ages. My old car from 2010 had a little digital clock. What's changed?
I think it's two things, scale and complexity. We are now, in 2026, looking at vehicles that run on over 150 million lines of code.
Okay, 150 million. Put that number in context for me.
All right, think of one of the most complex machines humanity builds. A modern fighter jet, like an F-35.
Okay.
Incredibly sophisticated piece of hardware that runs on about 25 million lines of code.
So a premium car is 6 times more complex, software-wise, than a fighter jet.
6 times. And the crisis comes from how the industry has traditionally tried to manage that complexity.
Which is the waterfall method.
Exactly, the dreaded waterfall. In the old automotive world, everything is sequential, linear. Step 1, you design the car's body. Step 2, you spec out the hardware, the little black boxes, the electronic control units or ECUs.
You go to a supplier and say, I need a box that does this and fits here.
And that supplier goes away for, 18 months, maybe 2 years, to design and build that specific piece of hardware.
And while they're doing that, what are the hundreds of software engineers doing?
Oh, they're sitting on their hands. Or, to be charitable, they're working on what we call low-fidelity models. They're basically writing code for a piece of hardware that does not exist. They're guessing.
And then the big day arrives. The A sample shows up in a box from the supplier. The physical ECU lands on the engineer's desk.
And it's almost always a disaster. This is what the report calls the late hardware bottleneck.
Right.
The software team finally loads their 18 months of work onto the actual chip, and nothing works. The memory layout is different, the timing is off, the chip has some weird quirk that wasn't in the spec sheet.
But the clock is ticking. You're deep into the project, maybe 6 months from the start of production.
And that's when crunch mode begins. You're burning millions of dollars a week, flying engineers around the world, trying to patch fundamental bugs. Features get cut, quality is compromised, and you end up launching a product that feels buggy and slow from day one.
It's what you could call the hardware hangover.
Right.
The whole company is suffering because you're addicted to touching the physical box before you can start real work.
That is a perfect way to put it. And these reports, they don't just admire the problem, they lay out a very clear path to curing that hangover. The solution is built on 3 core pillars.
Okay, lay them out, Ferris.
Pillar 1 is all about virtualization and a concept called bit parity. This is about breaking that addiction to physical hardware.
Got it.
Pillar 2 is the no-code revolution for the HMI, the user interface. This is about ending the war between designers and engineers.
And pillar 3.
Pillar 3 is standardization. It's about the data structures, the invisible plumbing that holds the entire software-defined vehicle together.
And then after we unpack those three, we're going to dive into the chip wars, the big fight between NVIDIA and Qualcomm, and finish with a look at the regional battlegrounds. Because what's happening in China is, well, it's a different world.
It's going to be a pretty dense session.
It is. Okay, let's dig into that first pillar, the strategic context. The report calls it the trap of hardware dependency. We've talked about the delays, but let's talk about the costs of delay. It's not just about paying engineers for overtime, is it?
No, not at all. It's about market relevance. By 2026, the car is a consumer electronics device, period. If you launch a brand new $60,000 EV, and the software feels like it's from 2023 because you had to lock the hardware specs 3 years ago, the customer feels it instantly. It smells old the second they drive it off the lot.
It's like buying the latest iPhone and finding out it runs on an operating system from 5 years ago.
Precisely. You'd feel cheated. And this leads directly to the concept of the software-defined vehicle, the SDV. This Electrobit paper has a great maturity model. It ranks car companies from level 0 to level 5.
And where does most of the traditional industry sit right now in early 2026?
Well, most of the big legacy brands, the Germans, the Americans, the Japanese, they are fighting tooth and nail just to get from what's called level 2 to level 3.
Okay, so what's level 2? What's holding them back?
Level 2 is updatable. It means you have over-the-air or OTA update capability. You can maybe fix a bug in the navigation system or update a map remotely. That's table stakes now.
But that's not what we mean by software-defined.
Not even close. The holy grail is level 4 or level 5. That's the innovation platform. And what that means is that the hardware and the software life cycles are completely 100% decoupled.
Decoupled, that's one of those consultant words. What does that actually look like in practice for an engineer?
It means I, as an app developer, can create a brand new feature for the car or completely redesign the user interface and push it out to the entire fleet of cars on the road without knowing or caring what specific silicon, what chip is running underneath.
As long as it meets the minimum performance requirements.
Exactly. It turns the car from a static object into a platform where new value is created after it's been sold.
It's funny. Right now, for most cars, the best day of its life is the day you drive it home.
Yeah.
From that point on, it just slowly degrades.
A level 5 SDV gets better over time. It gains new features, it gets faster, more personalized.
That's the dream. But to get there, you have to solve this virtual first problem. And that's pillar 1.
That's pillar 1.
Virtual first. On the surface, it sounds obvious. Just test your software in the cloud. We've been hearing this for years. Why is this being presented as a major breakthrough for 2026?
Because of a dirty little secret in the world of automotive simulation. For the longest time, cloud testing was, well, it was kind of a lie.
A lie. How so?
It all comes down to the underlying processor architecture. Your laptop and 99% of the servers in the cloud at AWS, Azure, Google, they run on by 86 architecture. That's the standard from Intel and AMD.
Right.
But your car, your phone, your infotainment system, it runs on ARM architecture.
Because it's more power efficient.
Exactly. ARM is designed for mobile and embedded systems where power consumption is critical. So for years, what happened was developers would write their code, compile it for x86 to test it in their cloud simulator, and they'd say, hey, look, it works great.
But that's not the end of the story.
No. Then they would have to do something called cross-compilation. They'd take the same source code and recompile it for the car's ARM chip.
And that's where the demons live.
That is the valley of death for software projects. Cross-compilation introduces all these subtle, maddening bugs. Maybe the way memory is aligned is slightly different. Maybe a low-level timing instruction behaves differently on ARM than it did on x86.
So you get the classic excuse, well, it worked on my simulator.
And the engineer isn't even lying. It did work on their simulator. But the simulator was a translation. It wasn't the real thing.
It's like reading a great novel in translation. You get the plot, but you lose all the nuance.
That is a perfect analogy. And in software, a lost nuance is a system crash on the highway.
So what's the breakthrough in 2026?
The breakthrough is a concept called bit parity.
Bit parity. Okay, break that down for me.
We are seeing a fundamental shift in the cloud itself. Amazon Web Services, for example, now has their Graviton processors.
And those are ARM-based.
Those are ARM chips running in the cloud, available for anyone to rent. This is a seismic shift. It means you can now develop and test using the exact same binary file in the cloud that will eventually run in the car.
So no translation.
No
Cross-compilation.
Zero. What you see is what you get. If it runs flawlessly on an AWS Graviton instance, you have extremely high confidence it will run flawlessly on the Qualcomm or NVIDIA ARM chip in the vehicle. This is what finally unlocks true cloud-native workflows for automotive.
So paint me a picture, a day in the life. What's a Tuesday morning like for a development team in the old world versus this new bit parity world?
Okay, old world. You've got a team of maybe 100 engineers, and you share maybe 10 physical test benches. You know what I'm talking about. Those messy desks covered in wires, circuit boards, power supplies.
The hardware lab?
Right. To test your latest code, you have to book a time slot on one of those benches. You might have to wait 3 days. You finally get 1 hour. You find a bug. You have to pack up, go back to your desk, try to fix it, and then get back in the queue.
It sounds agonizingly, painfully slow.
It is the definition of a bottleneck. Now, the new world in 2026, you're an engineer, you finish your feature, you commit your code at 5 p.m.,
And you go home.
you go home. While you're sleeping, the continuous integration system automatically spins up 5,000 virtual test instances on AWS Graviton. It runs the equivalent of 10 million miles of regression testing across every possible vehicle configuration.
5,000 instances.
Or 10,000 or 50,000. It doesn't matter. It's the cloud. It's elastic. You're just paying for the minutes you use.
So you come in the next morning.
You come in at 8 a.m., you grab your coffee, and there's a dashboard waiting for you. It shows you exactly where your code failed, in which specific edge case scenario with all the logs already attached. You can fix the bug before your 9 a.m. stand-up meeting.
That's the difference between being in maintenance mode and actually having development velocity.
It's a different universe.
But I want to push back a little. Simulating a CPU is one thing. But a modern car's cockpit isn't just one computer. It's a network of screens, right? There's the instrument cluster, the main IVI screen, a passenger display.
You're absolutely right. That's the next layer of this virtualization strategy. The report calls it simulating multi-screen topology.
Okay, fancy words.
It just means that today's car might have 5, 6, even 7 screens. They all have to talk to each other.
For example, I swipe a map from the center screen over to the instrument cluster in front of me.
Right. That's not just a graphical trick. That's a network message sent from one computer to another over a protocol, usually something called SOEP. Your virtual environment has to be able to simulate that entire network with all those screens all running inside a single cloud instance.
So the virtual computer in a server farm at Virginia is tricked into thinking it has 5 physical monitors attached to it.
Precisely. And this is where the VECU classification from the report becomes so important, because not all virtual ECUs are created equal.
I saw that chart. It had levels from 0 to 3.
Right. Level 0 is just a controller model. It's just the math. It's good for testing a single algorithm in isolation, but it's terrible for testing how a whole system works together.
So what's the sweet spot?
For 2026, the sweet spot, the Goldilocks zone, is level 3, host-compiled middleware.
Okay, unpack that term. Why is level 3 the right balance?
Because you aren't trying to simulate every single transistor on the chip. That's what a level 4 or 5 would do, and frankly, it's too slow for daily development work.
It's too accurate.
Exactly. Level 3 simulates the operating system, which is usually Android Automotive or QNX, and it simulates the key middleware services. It runs fast enough that an app developer can interact with it in real time, but it's accurate enough to catch 99% of the integration bugs before you ever touch hardware. It's the perfect trade-off between speed and precision.
Okay, that makes sense. So pillar 1 is get your teams off the physical hardware, get them into an ARM-based cloud, and use level 3 virtualization. Let's move to the front of the car. Pillar 2, the HMI, the human-machine interface.
The part the customer actually sees and touches.
Right, because you can have the most stable, bit-perfect back-end in the world, but if the screen looks dated or is frustrating to use, nobody's going to buy the car.
Or worse, if the menu system is so confusing that you get into an accident trying to turn on the defroster.
A real problem.
Yeah.
And the report talks about this fundamental conflict, the designer versus engineer conflict. This feels like a story as old as product development itself.
It's what the report calls the pixel-pushing bottleneck. Let me paint the picture. You have a team of brilliant, creative UI/UX designers in a studio in California. They're working in a tool like Figma. And they design this absolutely beautiful interface. It has subtle animations, perfect color gradients, custom fonts. It's a work of art.
They render a video of it, it looks amazing, and they send it over to the engineering team in Stuttgart or Detroit.
And the lead engineer opens this MP4 file or this PDF specification, and they just sigh. A deep, soul-crushing sigh.
Because now they have to try and recreate that piece of art. in code.
They have to manually write C++ or Kotlin code to draw a rectangle, give it a specific hex color code, position it at an exact XY coordinate, and then try to animate it.
And it never ever looks quite like the original design.
Never. So the designer comes back and says, "Can you just move that button 3 pixels to the left?" And the engineer says, "To do that, I have to recompile the entire software package. It'll take half a day. Submit a ticket."
And that friction just grinds everything to a halt. The designers stop trying to innovate because they know the engineers will just say no.
It kills creativity. So the 2026 strategy is about completely breaking that workflow. The report uses the term no code, which can sound like marketing fluff, but here it's actually real.
And it centers on a specific tool chain.
It does. The big player everyone is adopting is Google's Design Compose.
Okay, so how does Design Compose work? What does it do?
It creates a direct, unbreakable pipeline from the designer's canvas to the car's screen. The designer works in Figma, same as always, but they use a special plugin, a library of components.
Got it.
When they are happy with the design, they don't export a video, they hit a button that says Export to Compose. And that design is converted automatically into production-ready Android Jetpack Compose code.
So the engineer doesn't have to manually rewrite the UI from scratch.
Not at all. The UI effectively becomes what we call a pluggable resource. Think of it like a theme or a skin in a video game. The core logic of the application, the code that says, when this button is pressed, turn the air conditioning to 21 degrees, that lives in the main application, the APK.
But the look and feel of that button, its color, its shape, its font, is just a separate file that gets loaded in.
Exactly, and this enables massive flexibility. This is where we get into theming engines and something called runtime resource overlays, or RROs.
Okay, explain RRO to me like I'm a marketing executive, not an engineer.
Perfect. Imagine your car's dashboard is a coloring book. The lines in the book, the functionality, are drawn in permanent ink, but the colors you use to fill it in, those are on a transparent plastic sheet you lay on top.
You can swap out that plastic sheet at any time.
Instantly. So you can have a sport mode overlay where all the colors change to red and carbon fiber. You can have a comfort mode that's all soft blues and gentle animations.
Or a holiday theme that the marketing team pushes out in December.
Exactly. Or, and this is the billion-dollar use case for a big OEM like the VW Group, white labeling.
Ah, right. The same car platform, multiple brands.
You build one single, stable, validated software stack. One set of code for the navigation, the media player, the climate control. Then you apply a Porsche skin for the high-end sports car, an Audi skin for the premium sedan, and a Skoda skin for the value-focused model.
Underneath, it's the exact same code, just a different RO.
It's revolutionary. Before this, that would have been 3 entirely separate engineering teams duplicating work for years.
And to make all this work, you need something called design tokens. This term was all over the report, saying adoption is mandatory. What on earth is a design token?
A design token is a contract. It's a peace treaty between designers and engineers.
Okay.
In the old bad world, a developer would look at a design, see the color blue, and write color equals 0000FF in their code. They would hard code the value.
Which is brittle and dangerous.
Extremely. Because a year later, the brand director decides our new corporate blue is actually a slightly different shade, a bit more teal. The engineer then has to do a search and replace for every instance of that specific hex code across millions of lines of code.
And they will inevitably miss one. You'll have 2 different blues in the final product.
You always do. A design token fixes this. The token is just a variable name, an alias, like color.brand.primary.
So the engineer's code just says color.brand.primary.
They don't know what color that is. And more importantly, they don't care. Their job is to use the token.
And the definition of that token, the actual hex code, lives somewhere else.
It lives in a central file, maybe a JSON file, that is controlled by the design team. When the designer updates the primary brand color in Figma, that JSON file gets updated automatically. The build system sees the change, and every single app that uses that token is rebuilt with the new color. No engineer has to lift a finger.
It forces everyone to speak a common, shared language.
It removes all the magic numbers from the code. It sounds like a small technical detail, but it saves thousands upon thousands of hours of mind-numbing rework.
Okay, this is making a lot of sense. So we've virtualized the back end with Pillar 1. We've decoupled the front-end design with Pillar 2. But the car is still a physical machine. It generates data, vehicle speed, battery temperature, tire pressure, you name it. The application needs that data.
Right. And this brings us to Pillar 3. Data abstraction and middleware. This is the glue that holds it all together.
And reading these reports, this seems to be where a kind of culture war is happening inside these car
It
companies.
really is. It's a clash of civilizations.
You have the infotainment world, which is increasingly dominated by Android. It's written in Java and Kotlin. It moves fast. It expects things to be flexible and dynamic.
And then you have the deep embedded safety critical world, the world of AutoSAR. This is the code that controls your brakes, your steering. It's written in C++N. It's incredibly rigid, it's deterministic, and it must never, ever break.
And you can't just plug these two worlds together.
No, you'll cause an explosion. You need a translator. You need a diplomat.
You need middleware.
You need middleware. The report specifically calls out solutions like EB Corbos Link. Think of it as a secure translation layer that sits between the freewheeling world of Android and the rigid world of the vehicle network.
So what is it actually doing moment to moment?
An Android app, say a navigation app, says, hey, I need to know the current vehicle speed to estimate my arrival time. It sends that request to the middleware. The middleware takes that simple request and translates it into a very specific low-level network message, usually over a protocol like SOMIA-P, that the safety-critical computer can understand. The safety computer replies the speed is 100 kilometers per hour. The middleware then translates that raw data back into a format that the Java or Kotlin app can easily use.
But here's the problem I see. If Ford's safety computer calls the speed signal vehicle speeding kph, and BMW's computer calls it current velocity val, doesn't that mean my navigation app is still custom for each car?
You have hit on the absolute core of the problem. That is the trap of proprietary data silos. For decades, every car company invented their own names for everything.
So if I'm Spotify and I want to make my app's volume adjust with the car's speed, I have to write a custom version of my app for every single car brand.
Which is exactly why the app ecosystem for cars has been so terrible for so long. It's not profitable. This is the problem that Covisa VSS is designed to solve.
VSS, the Vehicle Signal Specification.
Right. It's a standard. It's an open source project where all the car makers, all the suppliers, all the software companies have come together and agreed on a common dictionary.
So they all agree that from now on, vehicle speed is called vehicle.speed, not car.vel, not speed01. It's vehicle.speed.
That's it. It sounds so simple, almost boring and bureaucratic. But its strategic importance is impossible to overstate.
Because it enables application portability.
The holy grail. If every car on the road speaks VSS, I can write one parking finder app, publish it to an app store, and have it work seamlessly on a Ford, a BMW, a Toyota, a Hyundai.
That's the app store for the car dream that people have been talking about for 15 years.
It is. And it's finally becoming possible because of tools that build on this standard, like the VHAL generator.
VHAL, what's that?
It's the vehicle hardware abstraction layer. It's the lowest level of the Android Automotive OS, the part that actually talks to the car's hardware via the middleware. In the past, engineers had to write the VHAL by hand. It was tedious, thousands of lines of boilerplate code, and very easy to make a mistake. Now, if you've defined all your car's data in the standard VSS format, you can use a VHAL generator to write all that code for you automatically.
There's that theme again. Automate the boring, error-prone stuff so engineers can focus on solving new problems.
That's the entire philosophy of the software-defined vehicle.
There was one more tool mentioned in this section of the report. SimFox. What does that do?
SimFox is a data injection tool, so let's connect the pillars. Remember Pillar 1, where you're testing your navigation app in a virtual environment in the cloud? Well, that app needs data. It needs to think the car is actually moving. If its GPS coordinates never change, the navigation logic will never engage.
So SimFox, it lies to the application.
It lies to the application in a very controlled and useful way.
Yes.
It injects a stream of fake sensor data into the virtual environment. It can simulate a whole drive from Berlin to Munich, complete with changing speeds, GPS coordinates, outside temperature, everything.
So you can test how your app behaves on a long road trip without ever leaving your desk.
Or run 1,000 virtual road trips overnight to look for bugs.
Okay, so we've built the complete software strategy. Virtual backend, decoupled front end, and standardized data. But all that amazing software needs silicon to run on.
It does. And that brings us to part 5, the hardware and the AI context, the chip wars.
And this report makes it pretty clear that by 2026, this has become a two-horse race.
It is a duopoly battle, and it is getting very, very heated.
In the red corner, you have the incumbent, the champion, Qualcomm.
Specifically with their SA8295 chip, that's the 4th generation Snapdragon Cockpit platform. If you sit in almost any premium EV that launched in 2024 or 2025, odds are it's running this piece of silicon.
Why has it been so dominant?
Because Qualcomm comes from the mobile world. They are masters of making powerful chips that are also incredibly power efficient, and they're brilliant at graphics. The AT295 can drive something like 11 different high-resolution screens simultaneously. For pure infotainment, it's a monster.
But in the green corner, we have the challenger, NVIDIA.
With a chip they have modestly named Drive Thor.
Thor. Yeah, they're not known for their subtlety.
They are not. And Thor is an absolute monster of a chip. The headline spec is 2000 TOPS.
Okay, TOPS. I see that acronym everywhere. What is it?
It stands for trillions of operations per second. It's a measure of AI processing power.
And 2000 is a lot.
To put that in perspective, a really good laptop with a neural processing unit might do 20 or 30 TOPS. Thor does 2000. It's a data center grade AI chip designed to go into a car.
Why on earth do you need that much power in a car? Are we meant to be mining Bitcoin on the way to work?
Like large. No, NVIDIA has a very different strategy from Qualcomm. Their big play is something called centralized compute.
Meaning?
Right now, a typical premium car has at least two powerful computers. You'll have one chip for the cockpit and infotainment, that's the Qualcomm chip, and you'll have a separate dedicated chip for ADS, the Advanced Driver Assistance Systems, the autonomous driving functions.
And you keep them separate for safety reasons. If your Spotify app crashes, you definitely don't want it to take the automatic emergency braking system down with it.
That is the traditional thinking.
Yeah.
But NVIDIA is saying, with Thor, our chip is so powerful and so well designed, you can run everything on this one single piece of silicon.
How do they guarantee safety?
Through virtualization and hypervisors, they create secure, walled-off partitions within the chip. So one set of cores might be running Android for the dashboard, while a completely separate, isolated set of cores is running a safety-certified OS like QNX for the self-driving AI.
That sounds incredibly efficient from a cost and wiring perspective, but also a little terrifying. It's a single point of failure.
That is the risk, and that's the debate raging in the industry. But the cost savings from removing multiple ECUs and all the associated cabling are enormous. And there's another reason you need 2000 TOPS.
That is.
The agentic shift. The rise of generative AI inside the car.
Okay, we're moving beyond just voice commands.
We're moving from a command model to an agent model.
Give me an example. What's the difference?
Command is what we have today. I say, hey car, I'm feeling cold. And the car's voice assistant parses that command and turns the heater up. Simple action, simple reaction.
And an agent.
An agent is proactive and contextual. The car's interior sensors notice my heart rate is a bit elevated. The cameras see that my posture is tense. It has access to my calendar, so it knows I just left a high-stress budget meeting. It checks the outside weather, it's cold and raining.
And it puts all that together.
It synthesizes all that data and concludes the driver is stressed and cold. So it proactively softens the suspension settings, it changes the ambient lighting to a calming warm white, it turns on the heated seat and steering wheel, and it cues up my post-meeting decompression playlist.
All without me saying a single word.
That's an agent, and to do that kind of reasoning, you need to run a powerful large language model, an LLM, locally in the car.
This is edge AI. You can't send all that biometric data to the cloud for processing.
It's too slow, and it would be a privacy nightmare. The reasoning has to happen on the edge, in the car, and that burns a phenomenal number of compute cycles.
That's what eats up the 2000 TOPS.
That's what eats TOPS for breakfast, which in turn is driving hardware trends for the displays themselves.
To show me what this agent is thinking, I need more screen real estate.
You need pillar-to-pillar, or P2P, screens. We're talking a single piece of glass that's over 50 inches wide, stretching across the entire dashboard. The car is becoming so intelligent, it needs a huge canvas to communicate its intent to the driver.
Okay, let's zoom out from the tech and look at the globe, because technology doesn't develop in a vacuum. The report has a fascinating breakdown of the competitive landscape by region: China, Europe, and North America.
And they could not be more different in their priorities.
Let's start with the one that's clearly giving all the Western CEOs nightmares: China.
The report calls China the velocity market, and the speed of development there it's almost frightening to watch from the outside.
How fast are we talking about?
A traditional Western OEM, like a Ford or a Volkswagen, typically takes around 40, maybe even 48 months to develop a new car from a clean sheet of paper.
4 years.
In China, the new EV startups are doing it in 18 to 24 months.
They are literally twice as fast. How is that even possible? Are they just cutting corners on safety and quality?
Not necessarily. They're just built differently organizationally. They are software companies first, They treat the car as a consumer electronics gadget that happens to have wheels. The phrase they use is the living room on wheels.
I've seen some of the videos. They have karaoke machines, built-in gaming consoles.
They're integrating high-end gaming engines like Unreal Engine directly into the dashboard UI to create these incredible 3D visualizations. And critically, they have deep, seamless integration with the phone ecosystem.
Right. Companies like Xiaomi and Huawei, they make the phone and they make the car.
So the integration is perfect.
Yeah.
You get in the car, and it's not like clunky old CarPlay. Your entire phone experience is just there on the big screen instantly. There is zero friction.
Okay, now let's contrast that extreme speed with Europe.
If China is the velocity market, Europe is the regulatory market. The focus is completely different. The biggest topic dominating the conversation there is the EU Data Act.
And this is all about who owns the data that the car generates.
That's right. The EU is basically mandating that the user, the car's owner, is the ultimate owner of the data, and they have the right to force the manufacturer to share that data with a third party of their choosing.
So if I want my trusted independent repair shop to see my car's diagnostic data, a company like Mercedes or BMW has to provide them with access.
In theory, yes. It's a direct assault on the walled garden business model, where the OEM wants to lock you into their expensive dealer network for all servicing.
And there's also a safety backlash against touchscreens happening in Europe, right?
A big one. It's being called the phygital trend, a mix of physical and digital. Euro NCAP, which is the main safety rating agency, has started to give lower safety scores to cars that bury basic, essential functions inside touchscreen menus. Things like hazard lights, wipers, turn signals.
Thank goodness. I mean, trying to jab at a tiny icon on a touchscreen to turn on your wipers while you're driving in a sudden downpour is just a terrible idea.
It's a death wish. So we're seeing a major trend back towards physical buttons and rotary dials for core driving functions. Use tactile controls for safety and use the beautiful digital screens for content and infotainment.
Okay, and that brings us to the third region, North America.
The report calls North America the service market. Here, the strategic focus is all on the subscription model. And the poster child for the strategy is General Motors.
With their controversial decision to drop Apple CarPlay and Android Auto.
A hugely bold and frankly very risky move. Starting with their new EVs, they no longer support phone projection at all.
Why would you deliberately alienate something like 90% of your customers who expect and love that feature?
It comes down to two things: data and dollars. If a customer is using CarPlay, Apple owns that customer relationship. Apple gets all the valuable data about where you go, what you listen to. GM just provides a dumb screen for Apple software to run on.
And GM wants to own that relationship.
They want to own the data, and they want to be the ones to sell you a subscription for their navigation service, their in-car apps, their premium features. It's a high-stakes gamble to control the future revenue stream.
And the report also notes that North America is where the cloud giants AWS and Azure have the deepest penetration into the automotive back-end strategies.
It's their home turf. Their
Wow.
influence is strongest there.
Okay. We have covered a massive amount of ground. The crisis, the three pillars of the solution, the chip wars, the global landscape. But we promised our listener, our client, a real strategy report. We have to give them the Monday morning action plan.
Right. This is the so what section. What do you actually do when you walk into your office tomorrow?
The report concludes with 4 very direct, very clear recommendations. Let's go through them. Recommendation number 1.
Virtual first mandate. And they mean a mandate from the very top of the company. You issue a new policy. No hardware is required for the first 9 to 12 months of any new vehicle program.
Oof. That's going to be tough.
Wow.
Engineers love to get their hands on the hardware.
You have to take their toys away. It's the only way. If your teams are sitting around waiting for a circuit board to arrive from a supplier, you're failing. You're burning money and time. Force them to use the cloud instances. It is the only way to truly decouple the development timelines.
Okay, tough but necessary. Recommendation 2.
Adopt design tokens immediately. This is aimed at the HMI and user experience teams. You have to force that contract between the design studio and the engineering floor.
No more magic numbers in the code.
If a code review comes up and I see a hard-coded hex color or a pixel dimension, it's an automatic rejection. Make them use the token system. It is the only scalable way to manage the complexity of multiple vehicle brands, trims, and software themes.
Makes sense. Recommendation number 3.
Data standardization. This is simple. Adopt Covisa VSS right now, today.
Don't invent your own internal language for vehicle data.
Stop it. Get over your not invented here syndrome. Every engineering hour you spend building and maintaining a proprietary internal data dictionary in 2026 is an hour wasted. You are building technical debt that will cost a fortune to unwind later. Use the open standard.
And the final recommendation, number 4.
Cloud scale testing. You cannot manually test your way to the level of quality that customers now expect from their software. It is impossible.
We talked about this, the nightly builds, the thousands of virtual instances.
Right. The report mentions using stability analytics partners like the company Profilins. Their whole job is to help you hunt for the Heisenbugs.
Heisenbugs, I love that name.
They're named after the Heisenberg uncertainty principle. These are the bugs that seem to disappear the moment you try to observe them.
Or, more practically, the bugs that only show up after the system has been running for 50 hours straight. A slow memory leak, a rare race condition.
You will never find those on a physical test bench that gets rebooted every morning by the next engineer. The only way to find them is to run 5,000 cloud instances continuously for a week straight and analyze the data.
Okay, so to synthesize this entire, very dense deep dive.
It really comes back to that MECE structure. Pillar 1, virtualize the back end, which gives you speed. Pillar 2, decouple the front end, which gives you flexibility. And pillar 3, standardize the data, which gives you scalability.
Speed, flexibility, and scalability. And if you're an automaker and you fail to do these things,
Then you are just a really good metal-bending company in a world that is now run by software. I think the final provocative thought I'd leave our listener with is this.
go on.
The car is no longer a vehicle, it has become a software platform on wheels. The companies that win in the 2030s won't be the ones with the tightest panel gaps or the most luxurious leather stitching.
We'll be the ones with the most efficient compiler.
The winners will be the companies that treat their software organization as their core product and the car as just the device that delivers it. If you're not a world-class software company today, you will not be a car company at all tomorrow.
That is a very sobering thought to end on. To our listener, our client, you have the report, you have the blueprint. The hardware era is over. Long live the code. Thanks for diving deep with us today.
Now it's time to get to work.